Number 10. In sampling from a normal distribution with a variance of 25, how large must the sample size be so that the length of a 95% confidence interval for the mean is 1.96? Okay, in problem 10, we want the length of the confidence interval to be 1.96. And this is the formula for a confidence interval. And note that sigma is known, so it's going to be a z. But the length is the top minus the bottom, which ends up just being twice this. So twice the air term, we want to be 1.96. You plug in z sub alpha over 2, which is 1.96. Those cancel, you solve for n, you get n equal to 100. Problem 11. Given the 5 pairs of points, what line of the form y equal x plus b best fits the data by the method of least squares? Problem 11, we want to find the least squares estimator of 5 observations, and this was the form of the line that we want to find the least squares estimator of b here. So you take the sum of the differences between our data and our proposed line, square it, add them up. We're going to call that L. So we're going to take the derivative with respect to beta. So the 2 comes out front, it's 1 minus that, and then times the derivative of b in here, which is minus 1. You set it equal to 0. You distribute the 2 and the minus 1, distribute the sums, solve for beta, plug it in our equation, put the sum of the yi's, the sum of the xi's over 5 equals 8/5, so the least squares line is y equal to x plus 8 over 5. Problem 12. What are the mean, median, and mode, respectively, for the density function f of x equal to? So here, number 12 is one of those problems that we're asked to find the mean, median, and mode of a certain distribution. And on test day, it's really best that you recognize that it's a standard Cauchy distribution, where you just instantly know that the mode is 0, the median is 0, and the mean doesn't exist. And but we're going to derive them from first principles just for fun. But also the Cauchy distribution is such an interesting distribution where the central limit theorem doesn't apply. So you can add up the sum of xi's from a Cauchy, and it doesn't limit to a normal distribution. So this is one of the distributions where the requirement of the variance is finite, plays an important role. Anyway, on to finding the median. So we want we want to go from negative infinity to some value m, which we're going to call the median. We want it to equal 0.5. Here's our distribution. We're going to make a substitution in for x. We're just going to let x equal the tangent of u, which is the sine. And the derivatives, we get this. Plug those in. So x squared, you square those, sine squared, cosine squared, and then we make that substitution here. Then you can combine this fraction into cosine squared plus sine squared, which is 1 over cosine squared. Invert, multiply, those cancel, leaving just 1 over pi. So then the integral of that is 1 over pi u, but I didn't put the limits of integration. Let's bring it back to the x world. So n for u is going to be the arctangent of x, and we're going from 0 to m. So if you plug in these values here, then we get this, and this limits to negative pi over 2, so you plug that in, and then distribute the 1 over pi, you get arc tan of m over pi plus a half. But remember that it equals 1/2. That's what we started with. So this implies 1/2 is equal to this. Those cancel, take up pi. So arctan of m is 0. Well, that implies that m is 0. So the median is 0. The mode is the maximum value. So we take the derivative of it, and we get this. Set it to 0. It implies that x equals 0. So the mode is 0. The median is 0. The mean is the expected value of x, so we plug in, we put the x, times the density. We make a u substitution, take its derivative, take the integral, we get log of 1 plus x squared, integrating from negative infinity to infinity, but you end up with an infinity minus an infinity solution, which is undefined. Number 13, a box contains 4 $10 bills, 6 $5 bills, and 2 $1 bills. 2 bills are taken at random from the box without replacement. What is the probability that both bills will be of the same denomination? Problem 13. Here we're going to take 2 bills at random. We're going to let x1 be the outcome of the first one and x2 be the outcome of the second. We want to find the probability that the 2 bills are the same. Well, the only way they can be the same is if they both equal a $1 bill, or they both equal a $5 bill, or they both equal a $10 bill. Well, we can find those probabilities. The 2 choose 2 over the 12 choose 2, and here is 6 choose 2 over 12 choose 2. And then that equals 22 over 6, which is 1/3. Problem 14. If the independent random variables x and y have marginal uniform distributions on the interval from 0 to 2, what is the probability that x squared plus y squared is less than 1? Number 14. This is also another one where I'm going to provide 2 solutions, but on test day it's best that you figure out number 1 here. So it's a uniform distribution, x and y, from 0 to 2, and the density is 1/4. So over this region, it's a flat surface, okay, and that plays an important part here. So now we want to be within this circle area here, but it's only a quarter circle that we want. So the probability that we're within there, and because the joint PDF is flat over this region, we can find the area of that semicircle divided by the total area of the region, which is we want 1/4 of the area of the circle divided by the total area of the region. So it's 1/4 pi over 4, which ends up being pi over 16. But now if you don't realize that and you integrate, this is the second solution. So we want to integrate from 0 to 1 minus x squared, or the square root of that, from 0 to 1. And our density is 1/4. So then I'm going to integrate with respect to y first, so that's y, and then we're going to plug in the limits here, and we get this. Now we're going to make a substitution where x equals sine of u. So the derivative of x is cosine u du. So plug those in here. So 1 minus sine squared, that's going to be cosine squared to the 1/2, which is just going to be cosine, and then cosine times cosine is cosine squared. So this simplifies to this, but I still don't like the squared and the cosine, so I'm going to take another well-known formula, which is 1/2 plus 1/2 cosine 2u, and then that gets rid of that exponent in the cosine. So we have this. Now we're going to treat these as 2 separate integrals, since the integral of the sum is the sum of the integrals. So then this piece, there's it's a constant, so it's just u, and then we plug in limits of integration, but I'm going to leave those blank because I don't know what those are. I'm gonna bring it back to the x world. And so here we have 1/8 cosine 2u du. Now you can make another substitution in for the 2u, and you end up taking it a 1/2, and then you get a sine. So that's where the 16 comes from, is where this substitution into 2u here. So I don't know the limits of integration. Let's bring it back to the x world. Well, x is sine of u, so u is the arc sine of x. We're going from 0 to 1. Sine of 2 times the arc sine of x from 0 to 1. Note here that the arc sine of 1 is pi over 2, and the arc sine of 0 is 0. So you plug that knowledge in, you get 1/8 pi over 2, and then plus. So here, 0, 0, and then the sine of 0 is 0, and when it's a 1, it's pi over 2, which you end up just pi, but the sine of pi is also 0, so that goes to 0, and the answer is pi over 16, which is the same as what we got up there. Number 15, let theta 1 hat and theta 2 hat be unbiased estimators of theta. Suppose the variance of theta 1 hat is equal to 1, the variance of theta 2 hat is equal to 2, and the covariance of theta 1 hat and theta 2 hat equal to 1/2. What are the values of C1 and C2 for which the linear combination of C1 theta 1 hat plus C2 theta 2 hat is unbiased estimator of theta with minimum variance among unbiased estimators of this type? So problem 15, we're given a linear combination. We want it to be unbiased, and we want it to have minimum variance. So first let's take the expectation and see what we get. And since each of these are unbiased estimates, then we take it times each, and we just get C1 theta plus C2 theta. Factor out a theta. Now we want this to be unbiased, so we want this to equal theta. But the only way for that to happen is if C1 and C2 are equal to 1. They add to 1. So this is 1 and then theta. Now let's look at the variance. So the variance of C1 theta 1 squared plus C2 theta 2 squared is, since that's a constant, you bring it out squared and times theta 1 hat plus C2 squared theta, and then it's 2 times the covariance of C1 C2 times the covariance of that. Well, we're given these values here, so you plug those in, a 1, a 2, and a 1/2, and it simplifies to this. Now somehow we have to maximize that, but we're under the restriction that they have to add to 1. So let's take that knowledge, and C2 would be equal to 1 minus C1. So plug that into our equation, and we get this, which simplifies to this. Well, to minimize this, we are going to take the derivative with respect to C1 of this. So we get 4C1 minus 3, set it equal to 0, and we get C1 is the 3/4, but then because of our restriction, C2 has to be 1/4. Yep. And note that the second derivative is positive, which says that is a minimum. Problem 16. If x has a standard normal distribution and y equals e to the x, what is the kth moment of y? Problem 16, we want to find the kth moment of y. But y is e to the x. So we substitute that in, and then we just get e to the kx. Now x is a normal distribution. So the expected value of this is you take that value and then take it times the density. Well, this e can be combined into this, And so the 1/2 plays a part there, cancels that too. So it's minus kx. And then we're going to complete the square here. So we're going to add a k squared, subtract a k squared, and then that comes into x minus k squared, and then we still have our extra that we added. Well, this is all raised to the e, so that piece can be factored out. And then since this is a constant with respect to x, it can be moved to the front. Well, this is just the density of a normal distribution, which is 1. And so 1 times that is just e to the k squared divided by 2. Problem 17. Let x and y be continuous random variables with joint density function f of x, y equal to 2. What is the covariance of x and y? Problem 17. We want to find the covariance of x and y. So here, this is our region, and the formula, I guess I skipped down. The formula for covariance of xy is expected value of xy minus the mean of x times the mean of y. But to do that, we have to find the marginal distributions of x, marginal distribution of y. Then we find the mean of x, and you add it, put an x there times the density, integrate over all possible values, you get 1/3. Similarly, you can do that. The mean of y is 1/3. So the expected value of xy is, you put an x and a y times its density, or integrate over the whole region. Integrate with respect to y first, so you get xy squared, limits of integration, plug those in. Integrate with respect to x, from 0 to 1, plug those in, you get 1/12. So the covariance of x, y is this formula. Plug in the values we just derived, and you get minus 1/3. Problem 18. X has a density function of f of x equal to 2 times 1 minus x, and is equal to 0 elsewhere. What is the probability that the larger of two independent observations of x will exceed 1/2? So on 18, we want to find that the largest value, so that if this is an order statistic, y2 is greater than 1/2. But before we do that, let's find the probability that just a general x is less than 1/2. And you'll see why. So you integrate from 0 to 1/2 of our density. Integrates to this, 1 minus 1/4 equals 3/4. So now when we want to find that the largest value is greater than 1/2, then we can take 1 minus that the value is less than 1/2. So this piece is the same here. But when our largest value has to be less than 1/2, that implies that all of our observations have to be less than 1/2. And since we only have 2, so both x1 has to be less than 1/2 and x2 has to be less than 1/2. Well, the x1 and x2 are independent, so you can take the product of those. And then we just found the probability that x is less than 1/2, so we plug in 3/4 and 3/4, and then 1 minus that, you end up with 7/16.